All right, so let's see, where should I tee you up? Didn't do rank size rule. Yeah, let's. I think let's start here. Yeah, let's start here. So kind of recap from last time. We had this picture. What the heck's going on? Remember from Friday, we had a long weekend full of probably binge drinking and partying and see if anything's left of your brain cells. You see, yeah.
The more compact cities are, the less it gets.
The more, say that again?
More compact
It's not the more compact. That wouldn't be the right word to use. So are you trying to say what's going on here?
Yeah. The increasing population.
Yeah, and I guess you're right. This particular one has got it's the number of workers in a city. So the city, when you say the word compact, I think density. So how many human beings are there per square mile, right? So if we have 100,000 people in that box or 100,000 people in this box, that's a whole different thing going on, right? So when I think compact, I was thinking something like that. We'd usually be thinking density. But here we're just looking at workers in the city. The city might be able to continue to grow too, geographically. The city might have started here through a process that we'll learn later called annexation. A city can grow its boundaries and annex in this piece of ground. And so now the city of Ottawa looks like that. So the city can grow geographically as well. There's a process for that we'll learn later.
The graph shows also the utility gain from going from S, which has 1 million workers, to M, which has 2 million. But once it reaches that 2 million point, then it'll start to kind of go down. But it's still better than living in S if you move from S because you gain more utility.
Okay, Liz, you want to add on to that?
What I wrote is that cities may be too large, like on 70, and that's why it's decreasing. The cities cannot be too small.
Yeah. Okay, so and what was the thing about what was the claim that cities can't be too small? What was the reason that we wouldn't have a city of size S if there was multiple places for a region? The example we went through is suppose we've got 6 million people in a region and there's 6 cities of 1 million people each. The author argued that's not sustainable, that size of a city, having 6 cities of 1 million. And we're actually using this graph and some of the underlying assumptions to argue why that's not sustainable. And so what was the key that was going to happen if there was 6 cities in a region that all had 1 million? Yeah, that was part of it, yeah. So there's going to be maybe some changes happening. So commute cost was one part. Let's play with that. In terms of happiness, utility, what does commute cost do? Does it make us happier or sadder? Sadder. So we got that competing thing. So we moved to the city because we're reducing our commute cost per house. So that makes us happier. But then as we move to the city, what do we run into? Congestion and construction and potholes and everything else or whatever. So we've got kind of the congestion factor offsetting the higher pay that we might get in the city from the agglomeration, the stuff that we talked about in previous chapters. So we want to move to the city. The city's got bigger opportunities. It's got more choices of entertainment options. It's got a lot going for it. But as we do that, there's also some competing factors that are going to reduce our utility. And so as we start to get over the M point, then our happiness might start to fall if the bad stuff the congestion starts to outweigh the pay or the benefits, right? So we kind of had 2 moving parts to our overall growth of the city. Okay, that still didn't answer why we wouldn't stay at S. Why wouldn't we stay? And did I see a question up or a hand for something else?
I have an answer for a response to that.
For the S? Okay.
Yeah. So the reason that you wouldn't stay at S, I believe this is what we talked about, is people would always move between the cities.
Yeah.
And so that's gonna fluctuate the size of it, and it's gonna cause one of the cities to be much larger than the other two, and everybody's gonna want to move to that city because the utility is greater.
So think about a reallocation. So if we're here and I'm a profit or a utility maximizer, if one person leaves that city and goes to another, the population grows. So one city is growing, moving this way, and because of the positive agglomeration, higher wages, blah, 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 and not too much congestion yet, then there's a utility gain. But when I leave this other city, that population is getting smaller, and so utility is falling, which is going to cause another person to say, oh, I'm going to move to that city too. And then the city gets smaller and smaller, and so this city starts shrinking as people leave it to go to the city that's growing. And so on this side of the utility mountain, it's not sustainable. That's not where we see a city. So cities can't be too small, is what I think Liz led us off with, because they're not going to exist over the long haul. Cities are going to continue to grow until the congestion, the bad parts, start bumping up against the good parts, and utility starts to fall. So cities are going to find themselves on the downward sloping side of utility mountain here in terms of the happiness per person in the bigger city. So we expect L to be a sustainable point for a city, because now if the person leaves the city to go to another city, the one city they're not going to want to go to because they're going to become less happy, and when they leave that city, they become more happy, and so they're like, oops, I made a mistake, I should go back to the city, right? So it's a sustainable point. Okay, questions on that? Let's just kind of review what we did last time. Chapter 7. Okay, so we went through a few models. I got a few more here. This is where we really left off with. We can start to think of small cities and medium cities and large cities, and the Nash equilibrium means what? Yes, but I want you to word it a little bit differently. It's not that there's no gain. I mean, there could be a gain, but what is the Nash equilibrium, Eddie?
At that point, until you're indifferent between cities.
And why are you like indifferent? What was the thing about the unilateral business with Nash equilibrium? Nash equilibrium, taking as given somebody.
So if your neighbor moves to a different city than you.
No, you kind of started off, you're on the right track, but you started off wrong. So a Nash equilibrium is a situation where nobody has incentive to make a move, taking as given what their neighbor's doing. So you assume your neighbor's staying put, and you say, could I do something to better my life? Right? Could I do something to better my life? And so here with this allocation, it's a Nash equilibrium because, as you could correctly pointed out, people are indifferent between the small city, the big city, and the others. So as we move to the big city, yeah, there's a lot of congestion, and so yeah, the small city doesn't have as much amenities, but I have less congestion, and so the utility, there's nobody wanting to shuffle between the big city and the small city in equilibrium. Okay, so Nash equilibrium. Let's write that down in your notes here, just in general. Nash equilibrium. So I'm going to give you apply the Nash concept in a lot of different ways, so it might be worded differently depending on what you're doing. But a Nash equilibrium is an outcome, or parentheses, set of choices, a set of choices. So you made a choice and you got an outcome, sometimes depending on how it's worded, but an outcome or a set of choices such that neither agent wishes to change your choice, taking as given the other's choice. So there's this idea of stability to it. Nobody wants to change their answer or change their choice, taking as given what the other ones are doing. So here, if you're currently living in the city, to move to a different city causes your happiness to go down. Right? So once you move to a different city, whether you move to this city, or somewhere, well, this is the way this one's depicted, I guess, it's 3 cities. So if you move, then you're moving, you're leaving here, you're adding a person here, so you're actually less than where you were. You're less than where you were. So you don't have an option that makes you better off, taken as given that other people are staying put in their city. And so it's a stable equilibrium. Okay, any questions or comments on that? All right, so the new material, or new section, different section than what we covered last time, analyzes the size of cities in different regions. And so we tend to see a really big city, like the first city is like a lot bigger than the next largest city. And so we really see that concentration. And so economists and geographers have tried to figure out that puzzle if there's some sort of rhyme or reason to it. And they came up with some consistency in the sizes in different places. So, leaving where we were before, locational equilibrium, a Nash, there's equal utilities across the 3 sides of the city. And so neither one wants to change where they're at. And so that's the picture we just did, all kind of one on top of each other. And here's what the, I guess, possible connection is. So there's this rank size rule, and the hypothesis was that rank times population tends to be constant across cities. What does that mean? If you're the largest population and you've got 12 million, then the second largest population is going to be 6 million. So ranking number 2 times 6 is 12. The third largest will equate to the largest city, so 3 times 4. And if you look at that graph and look at the rank, it would start to look like, oops, I'm going the wrong direction. Something along this picture. So 19 million, and then divided by 2, divided by 2, divided by 2, and so you have this fall off of kind of 3 really big cities, and then we get into a bunch of smaller cities as we go through it. All right, so then they set this thing up to test it. So the formula that was hypothesized was this one. Rank equals the size of the largest city divided by the population of the rank in that city. So if you're the second ranked city, then the prediction would be that your population is going to be half as much, because you're ranked number 2, you're going to be half as much as the big cities. And I don't think your book, I actually added a little bit of language because I didn't think your book was really clear. I thought they'd improve that from the first edition, but they really didn't. So if you want to write anything on your notes, put this formula, which is the same from your book, R equals C over N raised to the B power. And then just put C as the population of the largest city. Your book just says like C is a constant. You kind of have to guess with the way they do it. But C is the population of the big city. N is the population of some lesser populated city. And then the B is the exponent for the functional form that's to be estimated. So if B equals 1, this is like some number raised to the 1 power, what is 4 raised to the 1 power?
0?
No,
Or,
4 to the 1 power is 4. 45 to the 1 power, 45. So it's the same number. So if B is equal to 1, then the kind of the model would hold tight that we're going to have one city, let's say the one city has got 100 people, then the second largest city is going to have what population? So let's see, we've got 100 for the first city, the second largest city, and then what's that population going to be? This was n to the 1 power, it's 50.
So B will be given.
So B would be 50, and then this would be 25, and then this would be 12.5. This is just a math thing here. And so the function would look something like that, if B was equal to 1. Reality is not going to follow this math formula. It's just that's the hypothesis, that we seem to see cities that have these really big cities, and then they cut down really fast. And so that's this rank size rule. Okay, so here's some big cities. Tokyo, Mexico City, Sao Paulo. I actually did the Duolingo. I did my first little Spanish lesson yesterday. Buenos Aires, Santiago. Okay, so what is the predicted size of the second largest city near Tokyo? What would be the prediction from the rank size rule? Like 9.5, right? So that's all we're trying to test kind of is what is it really 9.5 million, the next largest city? And then you could do that for any of the major cities around the world. So this was kind of a puzzle that economists tried to figure out, like, why does it look that way? Okay, so here's what they found when they looked at different regions around the world. So the estimate in general came out to be 1.09. So it's close, but a little more even. In other words, with a 1.9, if you put this into a graphing calculator, it would flatten out a little bit. I'm exaggerating the effect, but it would be more evenly distributed, right? Rather than more radical of coming down. If it was 0.7, then the functional form would be more radical. If it was more evenly distributed, is what the data found. But there's different ways of defining a city. What's an economic city versus a political city? What do you think? Washington, D.C. versus something else? No.
You want actual places or?
Well, you can, I mean, you feel free to speculate, but I think we've got a really good example here near us, but Eddie?
Well, I was gonna say like a economically free city and then you could propaganda city.
No, that's not what they're getting at for this particular context. So it's not looking at that, right?
Earlier when we were discussing politics, and we talked about how the United States is more politically run than economically run.
Yes.
That's why we don't have charges for roads and stuff.
Yeah, so I mean that was used in a different context, but the political part, what is that part that makes it different here in terms of how we define the city? So one with boundaries by government, what is an economic city?
an economic city, Kansas City.
Kansas City. That's one I said was kind of near. So we've got, and they're all over the place. But this one's kind of obvious because we're sharing the border with Missouri, right? And so the economic city is kind of Kansas City metro, but the boundaries are political, like where the state line is or where the city line is. So if you use a political city, like if we just look at the city of Ottawa or the city of other ones, if we use it how government defined it, then we don't get as close as when we look at an economic city. So in this class, we're trying to see, well, what's the economics of the agglomeration and some of the other benefits. And so when we start defining a city or a region that way, we start to get a little bit closer to the ring size. Okay. Questions or comments there? All right. So what about more changes here? So the last section of chapter 7, or almost the last section, deals with growth, economic growth. So we've got an equilibrium starting at point I. Region's workforce is divided equally between 6 million. So we got 12 million people, 2 cities, 6 million each. They're both at I initially. Innovation in one city shifts the utility curve up. And assuming there's no migration yet. So nobody's moving from one city to the next, right? So we have the latest, greatest invention is invented in one of the cities. Does that tend to increase happiness in that city or decrease it? Increase it, right? Because there's more income generated, spillover benefits of the innovation, all that stuff. All right, so now the new city jumps up to point J in the absence of migration. Now take me from there using the model. What happens? We've got 2 cities now. One is at point I. The other city with the innovation is at point J. What happens using the logic that we've kind of been building up so far with migration? Dakota?
Some people are going to leave point I to go to point J of that city, and so is that other city going to?
Okay. So who's leaving where, I guess? You tell me. So I'm a person who's living at point I in the old city, the non-innovative city. What am I going to want to do?
Move to the other city.
Move to the other city. Now, when I move, what happens to point J in the innovation city? It goes to the right, right? So we're going to start sneaking along the J down that way, which then all of the citizens of that new innovative city, including myself, what happens to utility compared to a happiness of 80? It goes down. As I leave the old city, though, what happens to my old neighbors? It goes up. We start moving back. When does migration stop? When they're equal. When there's no more incentive. So the new Nash equilibrium looks like that previous picture we had. And who's made better off ultimately compared to 2 cities existing without innovation, 2 cities existing without innovation, who's made better off? The city without the innovation? Okay, that's true. I got you there for sure, right? Because we just said we moved from I up here. But the new city with the innovation is worse off?
We're going to go from 80 down to 75.
Okay, good.
It's going to go from 70 up to 75.
Okay, so at the end of the day, if we think about the starting point being 2 cities without innovation, starting at 70, what's true of people in all the cities? They're happier. So the innovation, once again, spreads to the whole city, to the whole region, which is so awesome about economics, right? It was a kind of a similar result we got from the production possibilities frontier. If we have beer and pizza and we have a new pizza machine, the production possibilities frontier shifts out. That means I might get myself some more beer out of the new pizza machine. That's a little bizarre at first. How did it happen?
Opportunity cost.
Opportunity cost was part of it, but I want more. The workers who were working here got freed up, and we were able to migrate, if you will, migrate to another use that made it less expensive for beer. And so we can have more of both. That's kind of what's going on here. Both cities get the benefit. All right, so that is good enough.